type of drink known as stout. When the drink is poured, it contains many spherical bubbles of gas which rise and form a foamy head at the top of the drink. The manufacturer of the drink state it takes 120 seconds for the head to form. A bubble, initially at rest, accelerates until it receives a uniform upward velocity. Explain the motion of the bubble. So this is a standard terminal velocity question, but it's happening upward. So initially, we've got a bubble under the water, and it's going to have two forces on it. It's going to have its weight force downwards, and it's going to have an upthrust force upwards. It's at rest, so that's it. Initially, there's only two forces. Upthrust, which I shall call U, and weight, which I shall call W. U is bigger than weight, so there is a resultant force upwards, and we can say from Newton's second law, that's F equals ma, the bubble will accelerate upwards. As the speed increases, drag increases. So now we have weight downwards, we have upthrust upwards, but we also now have drag, which is acting downwards. Speed increases, drag increases. Eventually, U is equal to W plus D. Eventually U is equal to W plus D. So there is no resultant force, and the bubble reaches a constant, or what we call terminal velocity. We're talking here about Newton's first law. Okay. So now we have this equation. For the smallest bubbles, the uniform upward velocity can be calculated using the equation. V is 2 rho stout minus rho gas r squared g over 9 eta. Derive this equation by considering the forces acting on the bubble. I'm going to draw a diagram down here of the bubble with a radius r. We've got the upthrust upwards, which is equal to the weight of the stout displaced. We've got the weight downwards, which is going to equal mg, which is the density of the gas, volume, that's mass, those two things added together equal mass, and g. The weight of the stout displaced is going to be the density of the stout, the volume, the gas, and the other thing we'll have is the drag, one equation for that, 6 pi eta rv, Stokes' law. So what we have essentially is at terminal velocity, upthrust is equal to weight plus drag. So what we have is rho stout Vg equals rho gas Vg plus 6 pi eta rv. Now for a ball, for a spherical bubble, V is 4/3 pi r cubed. So we've actually got here to take all of this and rearrange it to find little v. Little v is going to be big V G rho stout minus rho gas all over 6 pi eta r. So now let's put the volume in. 4 over 3 pi r cubed rho stout minus rho gas over 6 pi eta r, and do a little bit of tidying up. Oh, I've lost my G. Do a little bit of tidying up. The pi's can cancel. One of those can go, and the numbers can cancel a little bit. So we've got 3 times 3, so we've got 2 rho stout minus rho gas r squared G over 9 eta as required. So the one thing we have to assume for this whole equation is this thing, okay? This equation is only true when the flow of the liquid, so the liquid, as the bubble goes upwards, the liquid has got to flow downwards around it. Now we assume that this is a laminar flow. The stout flows with a laminar flow is the assumption. That's so we can assume that drag is 6 pi eta rv, but this is the assumption, that it's a laminar flow. Only if it's laminar can we use Stokes' law. Okay, the very last bit then now. Evaluate the statement from the manufacturer so it takes 120 seconds for the head to form. You should consider the time for the bubble to travel from the bottom of the glass to the top, height of the glass, density of stout, density of this, viscosity of stout, diameter of bubble. So we basically need to use this equation to find the terminal velocity. So we got 2 rho stout minus rho gas r squared G over 9 eta. Well, we're going to need to use 61 micrometers for my R. I've got the two densities, I've got and I've got the viscosity. So I've got 2 rho stout 2.06 times 10 to the minus 3 minus, sorry, wrong number, that one, 1.01 times 10 to the 3 minus 1.22 r squared, 61 times 10 to the minus 6 squared times 9.81 all over 9 times 2.06 times 10 to the minus 3. So 2 times 1.01 10 to the 3 and times 2 times 1.01 times 10 to the 3 minus 1.22 times 61 times 10 to the minus 6 squared times 9.81 divided by 9 divided by 2.6 times 10 to the minus 3 to give me a terminal velocity of 3.97 times 10 to the minus 3 meters per second. So now we've got the terminal velocity, we can find the time. So assuming a constant velocity, time is equal to distance over the velocity. The distance is 11.5 centimeters. And the velocity we've just worked out, 3.97 times 10 to the minus 3. So we have 28.95, so 29 seconds. So they think it takes 120 seconds. We've worked out that it actually only takes 29 seconds. So the assumption for the manufacturer's time is a lot more than our